An example of an LR discharge circuit is given in this problem. We have a 12-volt battery that's connected to an LR circuit for sufficient time so that a steady current flows through the resistor R equals 2.2 kiloohms and inductor L equals 18 millihenries. At t equals 0, the battery is removed from the circuit and the current decays exponentially through R. Determine the EMF across the inductor at time t, or as time t increases, and what time is E the greatest, and what is the maximum value in volts. So here we are given information. Our V battery is equal to 12 volts. The resistor is equal to 2.2 kiloohms, and that's just 2200 ohms. And the inductor is equal to 18 millihenries. Now the first clue that we have is that the current is steady. If the current is steady, then it means that the potential induced across the inductor is 0. So it's the maximum current that's flowing, and so in that case, the inductor at this point at t equals 0 minus looks like a short circuit. So it just looks like a piece of wire. Maybe that's a better way to put it. It just looks like a wire. So that means that the current going through the circuit is just going to be the V battery divided by the resistance, and that's 12 volts divided by 2200 ohms, and that's equal to 5.455 times 10 to the negative 3 amps, or that would be 5.455 milliamps. The timing, tau, is going to be equal to the inductance divided by the resistance, and that's 18 millihenry over 2200 ohms, and 18 millihenries is, we can rewrite that in terms of henries. That's 0.018, and that gives me a time of 182 times 10 to the negative 6th seconds, and that's also equal to 8.182 microseconds. And now we can write our formula for the current through the inductor is equal to I naught E to the negative t over tau, and that's 5.455 milliamps, e to the negative t over 8.182 microseconds. And the current through the resistor as a function of t, Actually, I forgot to write IL as a function of t. Is just going to be equal to IL function of t, and the potential induced is going to be equal to the current in time through the resistor times the resistance. And that's because the inductor only is going to provide enough current to maintain what it initially started out with, which was the current that we calculated with the steady state. And the maximum is going to occur at the beginning when this exponential is 1, and that happens at 0 seconds. And if we put that in, we'll find that it is 12 volts, which makes sense because that's the potential of the battery, and nothing has changed. The resistor is still the same. Had the resistor increased, then this potential would have to increase. If the resistance decreased, then the potential would have to decrease. But because the resistance stays the same in both cases, the induced potential is going to equal the potential of the battery at t equals 0 seconds when the switch is flipped.